nanohub.org.
Online simulation and more for nanotechnology.
Hello, everyone. Welcome to our first webinar. And yeah, my name is Alan Lee, and I'm associate professor at the Micron School of Material Science and Engineering, Boise State University in Idaho. You know that, and there are different computational modeling methods in the world, and so you can classify them in like in terms of the length scales and also the time scale. So today, the tools I'm going to show you actually is sitting at the far left, and which is based on the quantum mechanics. And so that means that it will simulate the smallest particle in the world. And so why we need to care about that? Because we want to study electronic property, right? And so that means we need to care about electrons and nuclei and how they arrange, how they interact with each other in the materials. And so for the quantum mechanics tools, and sometimes we also call it like Ab-Initios or first principle simulations. And they can calculate like electronic degree of freedom and interaction, bonding, and energy estimation. So once you get the energy, actually you can derive the energy like for a variety of the property, including electronic property, mechanical property, and magnetic property, etc. And so the governing equations and for those simulation tools is Schrodinger equations. And so the tool actually is to solve the Schrodinger equation and for wave function. And once you get the wave function, and then you can derive the equation from the wave function. So, and before we jump into the tool, and I want to give you a very, very brief introduction into a little bit quantum mechanics and also the DFT. The density functional theory. So we know like most of the physical property are predictable based on the quantum mechanics laws. And then the basic ingredient for that is the nuclei and electrons. So as I said, okay, the Gallium equation is a Schrodinger equation, and this is a very simple format. And you can see this is the Hamiltonian's operator and wave function, and which is a function of the electron position, nuclei position, and time. And E, this represents the total energy of the whole system or the material you want to simulate. And for the Hamiltonian operator, you can expand it into 4 different contributions. The first one is the kinetic energy of electrons. And then the other 3 are the potentials. So the potential for the electron-ion interaction, potential for electron-electron interaction, and potential for ion-ion interactions. So actually you see this equation is pretty complicated. So that's why if we need to deal with a many-body system, which means like if your material has a lot of electron, so that means that you need to deal with a lot of electron-electron interaction, electron-ion interaction, and ion-ion interaction. And so that this equation would turn into like not solvable. Well, use currents like based on our computational powers. And so that's why we need to use some kind of approximation. Like for example, this is one of the very popular approximation we use in the quantum mechanics is called density functional theory and DFT. And so what does the DFT try to do actually is like turn the many-body system, so you can think about like many electrons in your system, into non-interacting system under external potential. I really like this figure actually to simplify, okay, what the real system look like and what the DFT and try to approximate. So for the real system, if you have n electron, right, in your system, and then they interact with each other, so it's more like a human being, like all the human, just like holding hands in hands. And so you can break down the Hamiltonian in the Schrodinger equation is the kinetic energy plus a bunch of potentials. But like I said, if you have to deal with so many electrons, and this potential will be very complicated and will become a very complicated terms. And so for the DFT is like, they will turn this a human being, all those human being into a robot. So it means like they don't interact each other. And so that will be very simple, right, in your equations. And then they just like add the extra term, all those like potential into dump it into this external potentials. And so that means that you will have a 2 term only. One is the non-interacting kinetic energy and plus all the potential, like treated as external potentials. And so based on that approximations, and then this Schrodinger equation, we can break it down into another another like a format. And so including the Hamiltonian operators consist of the non-interacting kinetic energy, and then also the ion potential. And this term is called Hartree, is a mean field potential, which is for the mean field density. And then also this term is called exchange correlation potential, and which is to describe the electron-electron interaction. Sometimes we also call it correction potential. So I will show you a little bit more and what does it mean, exchange correlational functional, exchange correlational potential. And so all energy terms were written as a function of the electron density. So that means that you don't need to deal with like electron individually. You just need to deal with the electron density. So that will save a lot of computational time. So based on this, like these features, and then we can use it as a DFT and to determine the ground state ions and the electron configurations. And so I want to give you a little bit more detail about the exchange correlational functional, because in the tools I'm going to show you, and this is a very important like input parameter that you need to specify. So for the electron correlational functional, and there are two types of approximation you can choose normally in the tool, and one is called local density approximation. So it's a LDA, or generalized gradient approximation. So it's a GGA. So what is the difference between them? So like you see this curve actually represent the actual electron density. As I said before, electron density is very important because all the potential will be written as the function of electron density. And so to approximate the electron density will be a crucial part. And so so if you use LDA, and then the LDA actually use a flag function to approximate the actual electron density. If you choose like GGA, and it will include the flag potential and plus also the local gradient in the functions. And so probably you will ask me, okay, how can I choose like which one will work for my system? So it really depends on the material you want to simulate. Like if you want to simulate a box structures, and for example, like just like a pure metals or like a pure silicon, pure carbon. So you can imagine the electron density in your material doesn't change too much. And so we can use LDA to approximate it. But if you have like something, you have a dopant in it, or if you have a defect in it, and so you can imagine the electron density will like suddenly changed and in the material. And so that's why we need to include the local gradient in the electron density. So we will use like a GGA. So that's how we choose the exchange correlational functionals approximations. And so here I list like other like key DFT parameter you need to like specify in the tools you're going to simulate. And firstly is like the atomic coordinates of the structure you want to like simulate. And so normally you can specify as like probably Cartesians or fractional coordinates. So you will see that later in the tools. And then of course, the exchange correlational functional, and we call it like a correction term for the electron-electron interaction. So you can choose an LDA or GGA. And the third thing is called basis set, and is the set of the basic function and to represent electronic wave function. So in the world, actually, now there are two types of the basis sets. One is called Gaussian basic function. So it means I use a Gaussian function to approximate the electronics wave function. And then the other type is called plane wave expansion. So use a plane wave basis set like to approximate electronic wave function. The tool I'm going to use, I'm going to show you today actually is based on the Gaussian basic functions. And then another parameter called mesh cutoff, and which is an energy corresponds and to a finite 3D grid and for the calculation of electron density and the potentials. And so because you can see like the electron density and also the potential is a function of the position. And so that's why we have to define a grid and for them to sample the data. And so you can imagine if we increase the mesh cutoff, and so that means we will have a smaller spacing between the sample, and means that we will have like more dense 3D mesh. And that means we will have a more sample points and for the electron density and the potential. But of course, it will be more accurate, but it will cost more computational time. So it's always the trade-off like, okay, you want the accuracy, well, the trade-off between like accuracy and also computational time. So you don't want to have, very high accuracy, but you have to wait 100 million times, like 100 millions, like years to finish your job. So it's always kind of like a balance. And so based on all the features like approximation I told you, I described before, and so we can turn the Schrodinger equation into this, I call it like modified Schrodinger equation. So this is the first is the kinetics energy, so the non-interacting kinetic energy, and then this is the ion potential, and then the Hartree is a Hartree potential, which is is a potential for the mean density, electron density, and then this is the exchange-correlational functional potentials, and then this is the wave function for electrons. So you see, actually, I changed this. This is the little I, so it means it's referred to electrons, and this is the epsilon I. Actually, is the energy, and we need to calculate for the band structures. So we solve this equation and for the wave function, and once we get the wave function, and then we can use this a very simple equation to get the electron density. So for today's webinar, we focus on the electronic property. So that means that we need to calculate band structure, electronic band structure, and then to calculate electronic band structure, K-point sampling will be very important. So K-point actually density sampling in the first Brillouin zoom of the materials. And so if you have a higher K-point, more K-points, and then so of course probably you will see the curve in the band structure will be smoother. So you will not be able to see some big sharp, like big jump or big valley and that kind of thing. But if you, again, okay, if you have too many K-points, so that means it will take a longer time and to finish your calculation. And then, so it's always, again, it's like the trade-off between the accuracy and also the computational time. Okay, so maybe probably you still feel a little bit confused, and so don't worry. And when I show you the example, and that will help you understand better. So as I said, okay, Ab-Initio software, there are, and also Susan just talk about that. Okay, there are a lot of like Ab-Initio software available on the NanoHub, and then let me get into it and take a quick look. So this is the Ab-Initio software available on NanoHub, and you see this is the Ab-Init, and actually this is a plane wave basis set software package, and also have like a GW, and GW method actually can calculate a more accurate do a more accurate simulation. And then this is SIESTA, which this is the one I'm going to show you today, and which is a Gaussian, the basic set, based on the Gaussian data set. And also you see there are a variety of the software, the DFT software available and for the specific application. And also another popular, the Ab-Initio, the software is called Quantum Espressos, and that is a plane wave as well. And like for example, also have, if you want to do a Monte Carlo simulation, and then we also have like Monte Carlo's tools available here. And so it really depends on what type of system you want, and also how accurate you want. And so if you ask me, okay, which one is the best? There isn't, nothing is the best. I mean, some people prefer like Quantum Espresso, some people prefer SIESTA, some people prefer Ab-Init. It's like based on, okay, what your preference. So, okay, go back to the presentation. And then, so today I'm going to show you, this is the MIT Atomic Scales Modeling Toolkit. Actually, this is a toolkit, and why I choose this is because this have a very simple GUI, and also the student don't need to really like care about specify too many like input parameters, and so this will be very easy for them to jump into the simulation directly. And so that's why I choose the MIT Atomic Scale like Modeling Toolkits and in my class, and I will show you that later and how to use it. Okay, so. Okay, so SIESTA, we are going to use this tool called SIESTA, and then the input setups. And so firstly, you need to sign into a NanoHub, and before you can actually to access a tool, And then if you go to, and then once you sign in and go to your dashboard, and then in the tools, and then you can search this toolkits, and what you need to just like launch the tool, and then you will be able to see the tool. Okay, I'm going to show you that. Okay, so like for example, if I log in to my NanoHub account, okay, so if I go to the dashboard, okay, so I already have something running. So let me terminate it. Okay. So if you normally because I already run like some of the DFT tools, so that's why they keep the record here. But if you're a new user, and then I would suggest you go to the all tools and then just type in MIT, blah, blah. So just that's the second one pop up. And then I will strongly recommend you like select this hard. And so that means like it will be showing on your favorites and panels. And so next time you don't need to search it. And so hit this launch tool, and then they will and bring you to the MIT toolkits and panels. And so you see this application. And so if you click on so you see that this something show up. So here there's a variety of the applications. And so the ones I'm going to show you is this DFT for solid surface and molecules. So it's called SIESTA. So if you select that, and then it will bring you to this panel. So here, this is the panel the student need to specify the input. And so that's why I said it's very simple. So you don't need to worry about too many like parameter they need to understand and before they can jump into the simulations. And so today I'm going to show you one simple, a simple example. Like for example, if I want to simulate like this gallium arsenide band structures, and here this is the SIESTA input, and I'm going to specify for my simulation. So for the gallium arsenide, and you have a gallium and arsenide, and this is the crystal structures. And so my question for the student would be, okay, I want to analyze this gallium arsenide, the band structure, and then determine like firstly, okay, what is the band gap size? And then is it like this a direct or indirect band gaps? And so we can go back to this. Oh, sometimes it will like black out, and don't worry. So normally I would just like refresh my browser, and then this window will pop up again. So firstly, for the exchange-correlational functional, and if you click on here, you see this they have an LDA or GGA method approximation you can choose. And then so I say, okay, I choose the GGA. And then the run type, and I will choose, okay, you can do total energy or geometry optimization. So total energy is like, they will not do any like atomic relaxation. So, and you just want to know, okay, what is the total energy for this specific structures? And then so you can choose, so that's the total energy for. If you choose a geometry optimization, and actually that is for what the tool will do is like, okay, if your structure is like, you're not quite sure if the atoms, the atomic like position, the coordinates are correct. And so I want the system, actually the tool, to help me to find out the best position and for the atoms. And then I will choose a GGA. So we'll choose like a geometry optimizations. And then this one, this is the basic set. And here we have a 3. So this is very good. Like they will tell you, okay, this is a kind of like pool, a single zeta. Pool means like it will finish very quick, but you just get a very rough like result. And single zeta means I just use one single Gaussian to approximate your wave function. And then the double zeta, normally I choose this one, is like it will use like a 2 Gaussian function to approximate a wave function. And P stands for polarization. So it means that we also consider spin up and spin down effect in the simulation. And so normally I will just, okay, I choose the decent one, the double zeta with the polarization. And then, okay, and the next thing so we need to specify is the type of the system. And so you can choose like solid, surface, and molecule. So each of those like system, each type, and then they will pop up with a different example. And I will show you later. So here, okay, I just stick with the solids. And then I know the gallium arsenide is the phase center qubits. And so here, if you click on this example, and then you see they have a variety of examples actually available for you to choose. So why I liked it is because I can just use this example and as like a starting point. So what I need is just like probably modify the coordinate or modifies the atomic species. And then so I don't need to search, okay, what kind of coordinate they will be. And probably like, for example, if I choose like this time, I choose, okay, I start with the gallium arsenide, right? And then so you see actually the lattice type, lattice constant is already available there. So you don't need to go to, do some literature search and then to find out, okay, which one is which lattice constant is it for the gallium arsenide. So it will kind of save you a lot of time. But sometimes you say, hey, actually, if I want to do something similar to gallium arsenide, but I want to, but it's not real gallium arsenide, it's another kind of system. And then, but I don't want to look for like a lattice constant. Can the tool find it for me? Yes. So that's why we want to change this runtime to geometry optimization, because the tool will optimize the structure for you. So even this is like a little bit far away from the optimized structures. And so another one, I want to change it to, okay, the mesh cutoff and will be 300. I increase it, and because I want to do a band structure calculation, and normally the default like 100, and that will be good enough for if you just want to do like some geometry optimization, simple, like want to find out what is the best, the ground state, like structure, and for the material. But when I do the band structure calculation, I want to get them more accurate for the simulation. And then for the K point, so the default is a 4, and then so normally I would double it because of for band structure. So it means like I want to sample more K points in my Boolean zoom, and then I will be able to get, okay, see the curve actually is smoother, and I will not have like a big shot. And then again, okay, for the coordinate, so you see the coordinate already available. So here, this is the first line actually specify how many number of the atom in the unit cell. So you just need to simulate the unit cell. So here we say, okay, 2, and then we have a galliums and arsenides. And so you probably, when you look at my structure here, say, hey, there are more than 2 atoms in the unit cell. So don't forget, actually, this software, they will also consider space groups. And so it's not like the space group is not P1. And so they also have a space group. So that means that you just need to include, okay, one atom, and then so they will have a mirror atom and add it in immediately, automatically in the system. And so that is a very simple and then easy and for the student and to specify that. So they don't need to worry about, okay, what are the coordinates? They don't need to specify all the coordinates for individual atom. So after all this and double check, so like the Exchange-Correlational Functional GGA, runtime, geometry optimization, basic set, we choose a double zeta with the polarization, type of system solid, lattice type, phase center qubit, lattice constant, K point, and then, so this is a gallium arsenide, and the mesh cutoff is 300, and then we hit simulate. And so, and it will be very quick, and because it's only 2 atoms, and in the system. And so let's see. I hope it will run fast today. So, and here actually you see the output. And so this is what they're trying to do. Actually, the simulation is to optimize the electronics structures. So to find the optimized electronic density. And so once they found it, and then they will stop. So here, this is the output. You see they show you the total energy for the system. And you can also see the Fermi energy, they calculate it. And you get the position, the relaxed position, and also the forces like apply on the individual atom, lattice vector, stress vector, cell volume, etc. So if you click on this like arrow here, and actually you will get the XYZ coordinates. So this is in the Cartesians. And also the density of states. So you see here, this is a total density of states. And so this is a 0. So this red line represents the Fermi energies. And then so you see this is they have the band gap here. And also, I love something is very cool. It's called total and projected. If you click on this purple here, and you see actually this blue line show the total energy, and for the spin up plus the spin up and spin downs. And then also you see the Fermi energy, and also they break it down into, okay, what is the electron density for the Gallium? What is the electron density for the arsenide as well? So you can select, like, for example, and this one is the Galliums and spin up, spin down electron density. And this is the green line is the electron density, spin up, spin down, and for the arsenides. So that's a pretty cool, like the student also can, they have the scale here, and then they can roughly read, okay, what is the band gaps and for this material. And then they also have like band structure, you can plot it. And so the student can, okay, this is the band structure we get. And then so the student can just like download it. So hit this, right click, and you can save it as any format and anywhere, and the student want to. And then they also can print it out. And also another cool tool is like they have this like with the scale, and so the student can actually zoom into the individual band line and to measure the band gap to see, and also how the band alignment, analyze the band alignment as well, because the band alignment is very important for the electrical conductivity. So this is and if for this researcher, okay, they say, okay, I want to actually do some further study. I don't want to run on the Banano Hub, and they can even like download the SIESTA input file, and then they can submit it, use this input file and submit to any high performance computing facility. And so that is another way to do it. And so, okay, so this is one of the examples. And the other example I want to show, okay, before I show you another example, I want to summarize it. So the input file, like Exchange-Correlational Functional, the GGA we use, actually is to calculate this term and in the Hamiltonian, and we use the basis set DZP, double zeta polarization, to describe the wave function. And mesh cutoff, we use a 300, actually is a bit higher than the default, and because we want to calculate the band structures. And so again, if you larger cutoff and then smaller spacing and more dense of 3D mesh, it means that you get more sample point in the electron density and also the potential. So another here, because of the time, I'm not going through, okay, what the K-point sampling means. So I have some PowerPoint skits, kind of like some simple summaries and for the K-point sampling, because the student still very confused about the difference between real space and reciprocal space, and then K-point sampling. And so I do include like a very short YouTube video and to explain what this reciprocal space is, and then so why we need to care about the K-point sampling. And so that's a kind of like some quick note for students. And then another thing I want to show is that, okay, we know the gallium arsenide, and probably I want to show the student, okay, what happened if I change it? Like, for example, I changed the arsenide to another species in the same groups, and so that will be very easy to do it in these the nano hub. Like, for example, if we back to here, oh, sorry, the black light is so we need to flash it, and so we can go back to the input, and then just need to change this like AS to P, phosphide, and so. And then everything, we keep it the same. And so probably you say, hey, probably the lattice constant will not be the same or something. Don't worry. And then, so because the geometry optimization will find the lattice constant for you. So, but for here now, it just will take a little bit long time to find that like optimized lattice constant. And so here, because of the time, and so I just type it in the most, like the closest lattice constant, and for this system. So, and then I can, okay, hit simulate. So it will run again. And then, so because of the time, and I want to jump to the result. So what you will get something, okay, this is another band structure, and we just change one of the species. And then so you can show to the student, okay, see, okay, how different is it? Like very, very obvious, you can compare the band structure actually become bigger. And also but the band alignment look still very similar. So another thing we can show to the student is like, okay, if like, for example, if we want to simulate the graphene, okay, band structure, and that's a very, very typical like material we use in the semiconducting industry. And so in the NanoHub, actually, they do have the graphene sample. And so if we go back and then we can go to this example, and then you can see actually this is a graphene. And so the graphene sample is already available. So you don't need to change anything. You can just stick with it. And then also the student will say, oh yeah, this is a lattice type. We change it to hexagonal close pack now. And then the lattice constants are there and K points already there. So everything is like already set up. So very, very, very easy, and just need to hit, okay, simulate. And what I do actually is like I use this graphene to introduce about like the 2D materials, like a electronic property for the 2D material. And then I will ask the student, okay, after you get this graphene, what happens if I do some like doping? And then how the band structure will get changed. And so like one of the example I asked the student to do, so like for example, they will, from the NanoHub, they will get this band structure. And then we'll say, okay, how will the graphene band structure change if we dope with just one transition metal? So very simple. And then the student can choose, okay, whatever transition metal they like. Like for example, if a student, probably sometimes student will change it to, okay, what about we have a nickel? We dope nickel in there, but I don't know where the nickel will go to. So that's why, so the student can just stick with this geometry optimization, because the tool will find the best position for nickel. But the only thing we need to change, and also is okay, it's 3 atoms now. And then, so I just like, we can just roughly type in the positions, okay, because I don't know where the nickel will go. So I say, okay, what about I put it on top of this, like the second carbons, and 666, and then I roughly just like 0.1. So be careful, this is a fractional coordinate, okay? And so I don't know what will it look like. I'll say, okay, and then the tool will actually find the best position for you. And so it will run, and then actually at the end, and the student can pull out the XYZ coordinate, and then so they can use some kind of molecular software. If you have a question, we can talk about that more, what kind of software you can use to visualize the XYZ coordinates. And then also they can pull out the band structure. So at the end, they will be able to see actually probably the band gap will be closed, and because we have some electron we donated to the graphene, and then also the band alignment will look so different. Okay, so this is my last slide, and so some tips and for the teaching this modules, and why I choose this MIT Atomic Scale Modeling Toolkits, because simple GUI, input setup, very simple, very few input parameter. So you don't need to cover too much like computational theory before the student can jump into use those tools. And then we use this tool, normally I use this tool actually to create some in-class demo and to explain some abstract concept. And I also use it to like in the homework questions, and also I also ask the student to do a term project on it, especially now like they can do it like remotely. And then the courses I already use this to actually including of course the electrical property, and also use it in the thermodynamic class and the kinetic class, mechanical behavior, corrosion, nuclear, and structure of the material, and of course the intro to material science and engineering. I think that's it. If you have a more question, I think we are going to post this slides. And so here I have 2 YouTube video, and you can go to take a look at that. It's just to talk about some intro to the SIESTA. And then also I have a link for the additional resources I already posted on NanoHub. And more questions, feel free to ask me or email me. Thank you.